o'clock. It's a university event, so you'll need your name. Around here, like 10 minutes to 6, and you're not good at finding west, you can walk over with me. But otherwise, it's basically over that direction. And it'll go from 6 until 8 or 8:30 or something like that. It's a very pleasant space. It's the old president's house. Okay, so that's the dinner tonight. The other announcement is that on Friday, there will be an absolutely unofficial end of TASI event, okay? Absolutely unofficial. And it will happen, okay? So I'm not in charge of anything, okay? And it'll take place at the Rayback Collective, okay, which is someplace up on 28th Street in the part of Boulder that looks like the rest of America. I think some of you have been at Rayback already, okay? I'm going to show up there around 6 or something like that. It's one of these, it's an ex-plumbing supply place which has turned into a bar, and there are food courts, and there will be happy Boulder people sitting around drinking beer and eating food from food trucks. Okay, I haven't been there in 2 years, so I'm looking forward to going back there. So that's Friday, okay? So tonight, photo ID, name tag, Friday, absolutely unofficial. Okay, let's take it away.
Thanks. Okay, so I want to start by very quickly reminding you what the strong CP problem is. I know that Ben Safdie already briefly mentioned this in his lecture, so I don't want to linger on it long. And I think the best way to illustrate the strong CP problem that I've seen is a cartoon that came out of Anson Hook's TASI lectures from a few years back. Okay, so Anson drew this picture. You shouldn't take it too literally, but it's a cartoon of a neutron. What is a neutron? Well, it has 3 quarks inside, an up quark and 2 down quarks. And if you just draw a picture of an up quark and 2 down quarks inside some kind of bag, they have their electric charges, and in general, there is an electric dipole moment. The way to get rid of the electric dipole moment is to put them all in a perfectly straight line, so that the dipole from the up quark to that down quark cancels the dipole from the up quark to that down quark. And that seems pretty weird, right? So naively, if I just tell you a neutron is a bag containing an up quark and 2 down quarks, and I ask you to estimate what its electric dipole moment should be, you could draw this cartoon, and you would say, well, there ought to be a dipole moment which is roughly set by the size of the neutron. And if you draw this kind of angle, you would say, well, it should be something like 10 to the minus 16 times this angle theta in the units of E centimeters, which is what we measure electric dipole moments, and the E is just the electric coupling constant, which is about 0.3, so it's an order 1 number. This is what I mean by a dipole moment. It's this operator we could write in our effective Lagrangian. It's a coupling of the neutron to the photon. And people have tried to measure this, and no one has yet succeeded in measuring a non-zero value. Experiment tells us this number is less than something like 10 to the minus 26 E centimeters. And if we just compare these, that means that this angle is smaller than something like 10 to the minus 10. Okay, so that's the cartoon. But the cartoon is not inaccurate, even though it's a cartoon. And what's really going on is I could add this coupling in my Lagrangian. Okay, theta is a constant. It couples to gluons. That's what we talked about last time. I could have this term in the QCD Lagrangian. It violates CP or T. And it has physical effects, and this is one of the effects. Essentially, the angle theta in this cartoon basically is what this angle theta we can add to our Lagrangian does. Yeah?
It's not clear to me at this level how this term in the Lagrangian is related to that term.
Yeah, it's not clear, and it's actually hard to calculate precisely because basically this is some CP violating interaction of gluons. Then we have confinement. The quarks and gluons rearrange themselves into hadrons, and because that's a strongly coupled thing, it's hard to calculate. And so there are various strategies to kind of match QCD with this theta term onto some effective Lagrangian that has things like this in it. They all have some uncertainty in them. So we can kind of do these estimates at sort of the order 1 level. Maybe eventually lattice QCD calculations will tell us how to do this precisely, but so far I don't think they really have. Maybe Tom is shaking his head. So
It's going to be an order 1 correction.
yeah.
10 to the minus 10 is 10 to the minus 10.
Yeah. So we don't really know the number very precisely, but that's why I wrote this with a squiggle in it. It's less than or around 10 to the minus 10, and it's hard to say exactly where. But it's definitely not 1, and it's definitely not 10 to the minus 5. It's really, really small. OK, so that's the strong CP problem. Why is this number so small? Okay, it has the same flavor. Maybe flavor is not the right word to use. It has the same character as a lot of the other things we worry about in the standard model, like the electroweak hierarchy problem, the cosmological constant problem, or the flavor puzzle that Wolfgang was telling you about. It's a number. It's really small. We don't know why. We would like to know why. And there are basically 3 kind of big ideas people have had about this. There's a lot of papers on the strong CP problem. There might be some ideas that don't quite fall into the categories I'm going to say. But roughly speaking, there are 3. One is if the up quark had mass 0, really if any quark had mass 0, but the up quark is the lightest quark we know, so it's the one that's closest to 0, then this theta term would have no effect. And we'll see why along the way later. So for now, I'm just kind of asserting that. It will sort of fall out as a byproduct of something I'm going to show you in a minute. The second big idea is that CP is really an exact symmetry of nature. We do see CP violation in the CKM matrix, so it doesn't look like a symmetry of the world around us, but maybe it is a symmetry that was spontaneously broken. And maybe if you're really clever, you can construct some model where CP is spontaneously broken in a way that generates the CKM phase but doesn't generate a theta. And it turns out it's really hard. This category of models is known as Nelson bar models. The first paper was a single author paper written by Ann Nelson when she was a grad student. So Ann was the person who was clever enough to figure out how that might work. People have continued to study a lot of variations on this kind of model. But they're kind of baroque and kind of hard to make work. Like it's a nice idea, but when you try to really implement it and make it consistent with all the constraints, it's not easy. And unfortunately, I don't have time to do justice to Nelson bar models in my lectures. So I'm just telling you they exist. They are interesting. There's a lot of physics attached to them. But where we're headed is axions. Axions are, in my opinion, the most plausible solution to this problem. I think I forgot to say the massless up quark solution is actually disfavored just by precision data. So it's kind of a nice, elegant idea, but it doesn't seem to work in detail. OK, so axions have one big problem, which is called the quality problem. And one thing I want to do, hopefully by the end of this lecture, or at least the beginning of the next one, is tell you why I think the quality problem is actually not such a big deal as a lot of people make it out to be. OK, so what is an axion? An axion is a dynamical scalar field. It's periodic with period 2 pi. As I mentioned before, you should think of this as a gauge redundancy in our description. These are different labels for the same field. Not only does it have this periodic structure, it has an approximate continuous shift symmetry. Meaning if I change the value of theta, physics doesn't change a whole lot. And the dominant breaking of this shift symmetry comes from a coupling to gluons. Okay, so basically, all of the interesting physics of the Axion solution to the strong CP problem falls out of this action I have a kinetic term for the scalar. It has a dimensionful number in front f with units of mass. That's called the decay constant. Plays a similar role to the pion decay constant, if that's a familiar phrase to you. If not, this is just some mass scale. The reason I don't canonically normalize the field is I want to keep the period at 2 pi instead of 2 pi f, just for convenience. So instead of canonically normalizing, we have this extra factor in front. And then I have some integer over 8 pi squared integral theta times trace of the gluon field strength wedge itself. Okay, it has to be an integer for the reason that I was telling you about last time, because this is not invariant when we shift theta, but e to the I action is invariant because of the quantization of the integral of the trace of g wedge g. Okay, so we're just making use of the pieces we've been building along the way. So theta you should think of as not being a gauge invariant thing. But there are some gauge invariant operators. The derivative of theta is gauge invariant, because if I add a constant like 2 pi, I don't change the derivative. E to the I times an integer times theta is gauge invariant because of the periodicity of theta. So these things can appear in a Lagrangian without you having to worry about them. They're well-defined things. Theta appearing here is a little bit dangerous, and that's why it could only appear in the special topological term that has this quantization attached to it. Otherwise, it wouldn't have made sense. Okay. So this basically is the Axion solution to the strong CP problem. People usually introduce this by talking about something called a Peccei-Quinn symmetry. I'm going to come back to that. What I want to emphasize is really all we need is this effective Lagrangian. And if you can get this effective Lagrangian out of some theory, the solution is going to work no matter what your underlying theory looked like. Okay, and we're going to look at a couple of different kinds of underlying theories that both generate this in different ways. Yeah? Decay constant doesn't really have anything to do with decay. It's just some historical word people use. I don't really know why. There are models where it comes from the vev of something, or you could say it comes from the matrix element that makes this particle out of some current. There are different ways to talk about what it means, but yeah. For us, really, just think of it as that number in the Lagrangian. That's just what we call it. Okay, so I've told you that this solves the strong CP problem. Let me tell you why it solves the strong CP problem. So when I say that's the Axion action, what I mean is I'm adding this to the usual standard model action, right? So this is coupling to the standard model. QCD dynamics generates a potential V of theta. And V of theta looks okay, it better be periodic because adding 2 pi to theta doesn't mean anything. So we get a potential that looks something like this. And so the way this solves the strong CP problem is theta lives in this potential, and so the field is just going to relax to sit at the minimum. Okay, maybe Ben said some things about this in cosmology to you. In the early universe, this field might have been displaced from the minimum, stuck there by Hubble friction, and then at some point, when the expansion rate of the universe became small enough, the friction drops enough that it could start oscillating, and then it could kind of gradually redshift. And on average, it would be at 0 today. There might be still be some little oscillating bit around us, and that might be dark matter. So I think Ben said some of that to you. I am not going to talk about the dark matter phenomenology in this lecture. I just want to talk about the models. OK, so I've told you that QCD dynamics generates this potential. We can actually calculate this potential pretty precisely, and that's kind of surprising, because I already told you that it's hard to get from this theta term to something like the neutron EDM, because there's strong dynamics and we can't really calculate. You might think the same thing is true here, right? We coupled it to gluons, there's strong dynamics. How are we possibly going to calculate? But in fact, there's a clever trick, and it relies on the thing we were discussing at the end of the last class, which is the chiral anomaly. So here's the trick. I can remove this term from my action by doing a field redefinition. This is a field-dependent field redefinition. I'm going to take one of the chiral quarks in my theory, say some left-handed quark, and I'm going to replace it with e to the I n theta times the quark. So basically, everywhere this quark field appeared in my action, I'm going to plug in this expression. And so if I just do that in the action, I will generate some terms. I have a kinetic term for my quark that had a derivative in it. The derivative can now hit the theta and give me something that involves the derivative of theta. And so I can have couplings like a derivative of the axion field times a quark current. Depending on where my model came from originally, I might have already had some couplings like that in my Lagrangian, but I could get new ones through this operation. Yeah?
Is this field redefinition generic in all Axiom models, or is this a specific?
Yeah, this is something I'm doing just starting from that effective theory. We're going to see a different field redefinition when we actually talk about a particular model. So this trick is going to come up in multiple contexts. But here I'm just using that effective theory. So in particular, this is a standard model quark, not some other exotic heavy quark that we haven't seen. Yeah?
So when you ask just the black hole, so it seems that action has the decay constant plays a role in the mass, right?
No, it's not a mass because it's in front of a kinetic term. This term has derivatives of theta in it. Yeah. It will appear in the mass, and we'll get there in a few minutes. But yeah. OK, so we plug this in. Our quark kinetic term will generate some coupling. Our quark mass term, if I had a mass QL QR bar, that's going to turn into mass times e to the I n theta QL QR bar. So I'll get some dependence of the quark mass on the axion. Okay, so what was just a pure mass term before now is this field-dependent term that has a phase that knows about the axion. So these are two of the things I get. And the other thing I get from the anomaly, I get a minus n over 8 pi squared integral theta trace g wedge g. Because I did this rotation on just one chirality of quark, we have the Fujikawa path integral argument that says I don't get the whole answer just by looking at how my action changed. I have to look at how my measure changed. And that's where we ended up at the end of last class. Our measure changes basically by adding a new term to our action that looks like that. And so that cancels that. And what we've done is we've moved the axion interactions to the quarks. So we started out with them coupled to gluons. We've done a field redefinition. Now they couple to quarks. OK. Why was this useful? This was useful because we actually know quite a lot about how the quark mass terms appear at low energies when we talk about things like pion physics. Okay, and so we know how the quark mass matrix M appears in the chiral Lagrangian Okay, so the Chiral Lagrangian is a theory of some matrix valued field, which is e to the I pion field divided by some pion decay constant, f pi. And we know that the Chiral Lagrangian has terms in it that have the form quark mass matrix times this U dagger plus mass matrix dagger times U. There might be different conventions on which thing we call dagger and which things we don't, but at least in some convention, this is what we do. This mu in front is just some scale that is some measure of the size of chiral symmetry breaking in QCD. Did you see this maybe from a niche, or this has not been discussed at TASI? Okay, that's too bad. Then you just have to take my word for it. There is this effective theory of pions at low energies because they're Goldstone bosons. They can be packaged in this nice way, and you can just kind of use the symmetry structure of these Goldstones to write down all the possible terms. Okay, so maybe one thing that has come up at this TASI is Wolfgang talked about spurions for the flavor rotation symmetries. This is an example of that. We have the rotations of the left and right-handed quark fields in the low energy QCD Lagrangian, and the mass term, it's really just some set of numbers. But if you wanted to make it sort of officially invariant under those things, you would say the mass term transforms with some kind of rotations. And sorry, these are matrices, so I left out the trace, okay, to get a number out of this. The trace of the product of these matrices is invariant under those rotations if we think of this as a spurion. Yeah?
Is this redefinition of the mass matrix going to have any implications for the flavor mixing that Wolfgang was talking about in his last lecture?
It's not directly going to affect the flavor mixing, but it does give you this new field, which is the axion theta, which is going to itself mix with these fields. So there's kind of an extra pseudoscalar that mixes with all the other pseudoscalars and slightly changes their properties. The axion decay constant f, though, is going to be really big, a lot bigger than f pi. And what that means is that those mixing effects have very little effect on the pions themselves, or the kaons, or the other mesons. On the other hand, the mixing with those things will have some important effects for the axion. So if you're just interested in QCD physics, the axion effects are sort of small enough that unfortunately we can't see them. That's not a good way to discover the axion in general. But it is a good way to, thinking about these mixings is a good way to think about the axion physics. Okay, so basically, this thing exists in the Chiral Lagrangian where this U is a field, and these M's were just numbers. They were mass matrices. But what we've done is we've now made this M a field because we've made the masses dependent on theta. Okay, so inside this mass matrix, we now have theta appearing in the phases of some of the entries. And that means that if I expand this out, I will find terms in this inside this trace that depend on theta and don't depend on anything else, and those are a potential. Those generate some potential for theta. Okay. Okay, and so I've given you kind of a heuristic argument, but at least for those of you who have seen the Chiral Lagrangian before, you can actually do this calculation. It's worth working out. The potential looks like this. M pi squared f pi squared is the square root of 1 minus something involving a sine squared of a constant times theta. That's our periodic potential. And then this funny stuff in front involving quark masses. Question?
Do you know a good reference where this is worked out?
What was that?
The derivation of this potential in particular.
You said Shrednicki? Okay. So some lectures by Srednicki. Yeah, thanks. Yeah, I think it's at least mentioned in Anson's Tazi lectures from a few years ago, but I'm not sure if he worked out the details. Somewhat? Okay. Okay, so that's the potential. And oftentimes people write this as just some cosine of the axion, which has roughly the same shape, but in detail it's not that. It's this more complicated thing. Yeah. Right, so this is how the potential depends on the value of theta if we just set every other field to 0. Including the pion. If you expand this out, you will also find mass mixing terms between the pion and the eta and the other neutral pseudoscalars. That's right. So this is also the way that you derive the mass of the pion. Yeah. That's right. So in this expression, I've set all the pions and kaons and eta and everything to 0. But in principle, they are also there, and they have interesting mixing effects with the axion that you can also calculate when you expand this out. Yeah.
One question is that if you consider Dfsc Model, you consider more like eta mesons.
That's right. So we could make this U 2 by 2 if we're mostly thinking about just the up and down quarks, but you could also include the strange quark. You could include the. But the axion potential is basically the same. Basically, the strange quark is sort of heavy enough relative to the others that it doesn't affect this very much. Yeah. OK, and if you just expand this potential around the minimum, you find the axion mass. And if you plug in numbers for what the quark masses and the pion mass and the pion decay constant are, you find that the axion mass is about 6 microelectron volts if F over n is 10 to the 12 GeV. I haven't picked 10 to the 12 totally at random. That's roughly the number that gets you the right dark matter relic abundance, at least in the simplest cosmological history that you could talk about for the axion. OK, so that's roughly what we might expect this particle mass to be if it's dark matter. If it's not dark matter, or if the cosmology is more complicated, this F could take a wider range of values, and the mass scales inversely with F. But the thing I want to point out here that's related to the massless up-quark thing I said before is you'll notice that this formula goes to 0 if I send one of the quark masses to 0. In that case, the potential becomes perfectly flat. And the reason for that is that if I have a quark mass that's 0, I can do this chiral rotation, and I'll generate derivative couplings, but I won't have a mass like this, so I won't generate that coupling. OK, so in that limit, in fact, the physics becomes completely independent of the constant part of theta. All the physical effects come from derivatives of theta. And so whenever we have a massless quark, the theta term in our Lagrangian that we worried about for the strong CP problem basically becomes meaningless. It doesn't have any physical effect whatsoever. That's why if one of the quarks was exactly massless, we wouldn't have worried about strong CP in the first place. But because it seems like the quarks are not actually massless, we do worry about the problem. But that fact about the quark masses sort of reappears here. When you calculate the axion mass carefully, you see that it's proportional to something involving the quark masses. Yeah?
If the axion were discovered and it did indeed have a very, very small mass, would that introduce sort of a new hierarchy problem?
Actually not. Well, kind of. OK, that's kind of related to what I'm going to talk about. It's the axion quality problem. So let me come back and address that later. Yeah. But I guess I should say this contribution to the potential, this is just a totally finite potential, no divergences. So at least this contribution we don't worry about. But what you might worry about are other contributions. And that's what we'll come back to. Yeah.
F doesn't appear in the potential, but it appears in the mass. Where does that?
Good. So it appeared in the mass because to get the mass, I need to canonically normalize my field. So this is the potential written in terms of this theta, which is 2 pi periodic. But the actual canonically normalized field that has the usual like 1 over p squared minus m squared propagator is F times theta. And that's why the F appeared. Thanks. Yeah? At least in these QCD interactions, it appears as f over n. And for that reason, people sometimes call f over n the decay constant. Different literature, you might find slightly different conventions about which thing people refer to. But there could be different integers, like there could be a coupling to photons that has a different integer than that n. And so the ratio of those two integers can play an important physical role. The integer n also plays some physical role in cosmology when we think about domain walls, and that again is beyond what I'm going to have time to discuss. Yeah.
I mean, the potential n is equal to 1, right? In the potential you draw.
In the potential I drew here, right, good, thank you. I drew this in the minimal case n equals 1. Otherwise, the period would not quite match. Yeah.
N is equal to 2, like I could have like theta equal to pi, and would be that CP conserving?
Right, so if n is larger, then your potential oscillates faster and you'll have multiple minima, and they're degenerate. And that's why there can be domain walls in cosmology that go between these different vacua.
Yeah, I wonder like what happens to the dipole moment? Is it still like okay?
The dipole moment depends on this theta that I wrote here as a constant, and that's basically the same as n times theta over there. So that means that will not care if you have these n different vacua, they will all give you 0 dipole moment. Yeah. Thanks. Okay, good. One more. If n is negative, I guess this was really an absolute value. Yeah, thanks. Okay. Okay, so just a couple of brief remark I want to make about language. I've been calling this the axion. The word axion is sometimes used for more general fields that don't necessarily couple to gluons like this, but maybe have similar couplings to photons, like a theta f wedge f for photons. Some people reserve the word axion for one that solves strong CP and call the other things axion-like particles. Some people use the word axion for all these things and call this one the QCD axion. I'm just going to say the word axion in general. I'm mostly in these lectures going to be talking about strong CP, but just something to be aware of. If somebody says the word axion, they might or might not mean something this specific. The other thing to say is what's the difference between just an axion and a Goldstone boson? And I guess I would say, we could just talk about some periodic scalar and say very similar things. It could possibly have these couplings. I guess the main difference is we usually talk about axions as particles that are very light, much lighter than like pions. And we also tend to assume when we talk about axions that the dominant symmetry breaking effects we're interested in are the ones that come from this kind of coupling, as opposed to just random stuff that we write down. Yeah.
Have people thought about trying to solve the strong CP problem by adding a field that is not a scalar? Would that be possible?
People have tried all kinds of things. I'm not sure that I know any really effective solution that doesn't fall into basically one of these categories. Okay. Good. So that was sort of axions in general, right? So here we only use the low energy effective theory, coupling to gluons. I didn't tell you where the theta came from. I just wrote down the coupling. So now let's talk about kind of the classic model. This is a 4-dimensional renormalizable model that generates that effective theory. It's called Ksbz after Kim, who wrote a paper about the model, and Shipman, Weinstein, and Zakharov, who wrote a second paper basically at the same time. And this is some extension of the standard model. It involves a complex scalar field phi and 2 heavy quark fields Q, which is a triplet of SU3 color, q bar, which is a 3 bar, an anti-triplet of SU3 color. They're both left-handed Weyl fermions. I don't write a mass term for them, but I do write a Yukawa coupling, y phi q bar plus Hermitian conjugate. And then I write a potential that depends only on the magnitude of phi. Okay. That is the Ksbz Lagrangian. Let's analyze it. It has a classical global symmetry generated by two different U1s. One of these U1s rotates the field phi and rotates the field q in the opposite direction. One of these U1s rotates the field q and rotates the field q bar in the opposite direction. Okay, so again, q bar is just a name of the field. It's not a conjugate of q. So I have these two different symmetries. I can have other symmetries like one that rotates phi and one that rotates q bar, but I can get that by a combination of these two. So these are kind of two independent symmetries. And this first one has an ABJ anomaly. Okay, it's a chiral symmetry. It rotated one of our fermions and not the other fermion. And so it has the anomaly we talked about last. Lift this up. Okay. The key assumption of this model is that our potential has the classic symmetry breaking shape. Okay, so it's a function of the magnitude of phi, but it has a minimum, which is a circular valley that spontaneously breaks the U1. Spontaneously breaks the U1 PQ that acted on phi. Was there a question? Yeah.
Yeah, really basic question. Is phi the axiom here?
Not the axiom. I'm about to get to that. So, so what we're going to do is we're going to parametrize phi as 1/√2 times a number f plus a scalar s of x times e to the I theta of x. Okay, so theta is like the Goldstone mode that goes around this circle at the base of the potential. So the potential gives no mass to theta. And the mode S is the mode that goes up the hill away from the minimum. S is sometimes called a Saxion. This terminology kind of originated in supersymmetry, where people put S's in front of lots of things to mean the scalar that goes along with something else. But we could use that language even in the non-SUSY context here. This is a scalar that kind of came along with the axion. And theta is an axion. Okay, so that's the setup. Are there any questions about the setup here? No? Okay, so now what I want to do is just argue for you that this theory produces that theory as an effective theory at low energies. Okay, so so what we can do with this theory is integrate out our heavy fields. Yeah, I guess I'll just. We had this Yukawa coupling of phi to q and q bar. So that turns into a mass when we plug in the vacuum expectation value of phi. The mode S gets a mass If this was a quartic potential, it would be of the order square root of lambda times f, just like the Higgs mass that you're familiar with. And so Q, Q bar, and S are all heavy. Okay, let's take F to be much bigger than the QCD scale. So I don't have to worry about the strong dynamics. When I think about these heavy modes, I can just integrate them out. But I should be a little bit careful about that, because what I wrote here wasn't really quite right, because phi had a phase, right? So phi was not just f. It was really f e to the I theta in terms of our light field theta. Okay. So my mass term for the heavy quarks knows about this light field that sets the phase of the mass. And so if I want to integrate it out, I could do it with loop diagrams, but the kind of nicer, slicker way to do this is to say, well, I have this term in my Lagrangian. It has this phase that I don't like very much because I want to just get rid of these fields and forget about them. How can I get rid of that phase? Well, I can do a chiral field redefinition where I replace Q by e to the minus I theta times Q. Plug that in here, the phase goes away. Okay. So it's the same chiral field redefinition that we've done a couple of times now. What happens? We generate some term coupling theta to our gluons. In fact, there's some integer in front. I guess there's a 3 because there are 3 colors of these quarks. So we really did 3 different rephasings in terms of just counting the fields that appear in the Fujikawa argument. Is that right? That's not right. That's not a 3, sorry. What I actually get is a trace of the Dinkin index times 2. Yeah, sorry. I did not carefully prepare all the order 1 numbers in front. I think it's actually correct as written. It would be a 3 if I were doing photons. OK, sorry for muddling that. But that's the upshot. We can remove all our heavy fields. We keep our light field theta. It has a kinetic term that has this f in it because f was the magnitude of phi. So when I expand out, I also shouldn't have had a half here. So really don't trust me on order 1 factors. When I expand this out, I will get the 1/2 f squared d theta squared like I wanted. And I got the coupling of theta to the gluons by doing this field redefinition. And then theta doesn't talk to the heavy things, and I can just forget about them. Yeah?
Could you repeat again why the field redefinition gives you the gluon coupling?
That was the chiral anomaly from last time. So that came from either thinking about the path integral measure, which has to be carefully regulated and turned into something like this. Or it came from thinking about sort of having some current that created these quarks, and then they talk to the gluons. OK. So the chiral anomaly is a super useful trick. We saw that we used it both to understand the low energy theory by putting the phase into the light quark masses. And here we used it to understand how to get from the high energy to the low energy by taking the phase out of the heavy quark masses. OK, so if you want to work with axion physics, it's good to get comfortable with this, this way of rephasing your fields to kind of shuffle around these terms to where you want them. OK, so that is the Ksbz model, and that is kind of the baseline model of 4D axions. It's not the original one. The original one came from Peche and Quinn and Weinberg and Wilczek. The PQ that I called the symmetry came from Peche Quinn. But the Peche Quinn Weinberg Wilczek axion model basically involved sort of using the Higgs to play the role of a field like this. And so it basically pinned the scale f at the electroweak scale. And that was very quickly ruled out by data. And so several years later, the Ksbz model came along. And in this model, this scale has nothing to do with any scale that we already know about, so we're free to make it heavy and explain why we haven't seen these particles yet. There is another classic model called the Dfsc model, the Dine, Fischler, Srednicki, Zhitnitsky model. Again, that was 2 different papers, one by Df and S and one by Z. That model kind of combines elements of both. It has the Higgs's transform under U1 PQ, but it also has some complex scalar phi transform, and most of the PQ breaking lives in phi. It gives similar predictions, but it has slightly different numbers for what you expect some of the couplings to be. Yeah?
There's something counterintuitive here.
Mm-hmm.
To make the Q as heavy as I want,
Uh-huh.
this interaction doesn't get weaker.
This interaction actually does get weaker. What's going on here is I've normalized things in kind of the nice way from thinking about just the topology, that theta goes to theta plus 2 pi. And I've normalized my gluons by the kind of nicely quantized basis. But if I want to canonically normalize my fields, canonical normalization multiplies this. When I normalize the gluons, I get a factor of g strong squared. And when I normalize theta, I get a 1 over f. And so as I make these things heavier, I make f bigger. And that makes the canonically normalized coupling here smaller. The reason I like to write it this way is that this shows you it has this topological character that's quantized. These things are running and they have all the messy effects, but it's all, if you know how to renormalize the kinetic terms of the gluons and the axion, then you know these things. And so there's no kind of independent renormalization of this term when I write it that way. Okay, one more thing to say about this model. Let me just write it in the corner here. The minimal version of this model, I told you these things were color triplets. I didn't give them any electroweak charges. So you might say, well, the minimal version of this model, these things don't talk to electromagnetism at all. But they actually do, because in the low energy theory, there's a mixing. Again, if you unpack that chiral Lagrangian, there's a mixing of the axion with the neutral pion, and the neutral pion talks to photons. And so if you calculate, you'll find that there actually is kind of an effective theta f wedge f term that has a funny coefficient in front. It's roughly in these usual units where I would have expected to find an integer. I find something like minus 1.92. Looks like it's not an integer. It looks like it broke what I told you before. It doesn't really, because in fact, this is somehow proportional to the mass of the axion. So somehow this was really like a derivative squared of the axion, which after the potential is generated turns into something that depends on the mass. And the reason why it's relatively big is that the pion potential and the axion potential are generated by the same dynamics. So there's kind of an interesting story there. If I had more time, I would elaborate on it. But you should just be aware there is a coupling of the axion to photons in the minimal Ksbz model. And in fact, if you look at experimental plots where people are looking for the axion, they have some band. They usually draw some axis of like 1 over f versus axion mass. We saw the axion mass is proportional to 1 over f, so there's some band of predictions. And if we specifically make this the photon coupling, there's some line people draw within that band that's labeled Ksbz. And that photon coupling is this one. But what you can also see from this model is you can get lots of different couplings if you want, because I could have made these Qs carry charges under SU2 times U1 and just did the same thing. And everything that was relevant for strong CP would be the same, because the way they talk to gluons would be the same. So in fact, there's kind of a whole family of Ksbz-like models, and they give you different lines in that space. Okay, so there's a lot of model building freedom in terms of what number you get out. Yeah? You can't ever get rid of this, because the mixing with the pion is built into the very way that we generated the axion potential that came from that term in the chiral Lagrangian. So the same thing that generates the potential that we need to minimize to solve strong CP automatically does this too. Those contributions will be quantized. Those will have integers. And so those integers can never quite cancel this thing. They can almost cancel it, like 2 minus 1.92 is really small. So there's some sort of lower boundary. Yeah, but you never quite completely get rid of it. Okay. Good. So that's sort of what you should think of as like the minimal model for an axion. And this model is a good place to talk about the big problem. Okay, so if you talk to a lot of particle theorists who are model builders, they might tell you that, well, axions are kind of nice. They sort of almost want to solve the strong CP problem, but they have this big looming problem that is annoying and has to be dealt with. And we can see this problem just by thinking about terms we can add to this Lagrangian. Okay, so this Lagrangian had a global symmetry. Tomorrow, I'm going to tell you some reasons why you should not believe that global symmetries ever actually exist. Okay, so you could say, well, maybe there's an approximate global symmetry, but what if I write down some other term like phi to the n divided by, say, the Planck scale to the n minus 4? Okay, because I think at some level, something is going to break the symmetry. The Planck scale is kind of the highest energy scale we ever really care about. So maybe there's something like that. And this coefficient c can be a complex number. It's some magnitude times e to the I. Let me call it phi pq slash. The pq slash means this breaks the Peccei-Quinn symmetry. Okay, phi was charged under Peccei-Quinn, but if I rotate phi by some phase, I change this term. Okay. So what does that mean? Well, we've taken a symmetry that our theta was kind of an approximate Goldstone boson of. Again, it was never really a symmetry because it had an ABJ anomaly in the first place. And we needed that. We needed it not to be a symmetry to solve strong CP. But you might have thought maybe it's a really good symmetry, but this is some other source of symmetry breaking on top of the anomaly. Well, let's just calculate, right? So this phi, I don't care about this axion. Let's just write this as f over square root of 2 times e to the I theta and plug it in. What do we get? We get some term 2 times the absolute value of c m Planck to the 4th f over square root of 2 m Planck to the n cosine n theta plus phi pq. So any term that breaks the Peccei-Quinn symmetry is going to give a mass, going to generate a potential for our kind of would-be approximate Goldstone boson. And this potential in general could have a phase here. So its minimum may not be at 0. Okay? So in terms of this picture that I drew before, now we're going to have some other periodic potential, and maybe it's, say, minimized here. Maybe it has a different period. We're going to have some other contribution that we're adding onto this. And because of that, when I add these two potentials together, my minimum will not be at 0. And then when my field relaxes to its minimum, I'm going to have some effective theta angle, and I'm going to generate a neutron EDM. So what I need to do is make this new contribution really, really small, or have a really good explanation for why the minimum was lined up with that one, which isn't really obvious, because CP is not a good symmetry of our universe. Why shouldn't there have been a phase? And it has to be really small, because it has to be not only smaller than the original one, which depended on m pi squared, f pi squared, which are a lot smaller than the Planck scale. It has to be even much smaller than that because it can't just displace this by a little bit. It has to be less than 10 to the minus 10. Okay, so this is a really strong requirement on this new potential. Okay. So the basic problem here is we started with something exponentially small, right? Where does the QCD scale come from? It comes from the running of the QCD coupling. So it's some exponential e to the minus 8 pi squared over beta function coefficient times g squared, where g squared is your coupling at high energies. So we have an exponentially small potential, and we have this other contribution we might worry about, and it's not exponentially small. It's kind of power law small in f over m Planck. And so that's really dangerous, trying to beat an exponential with the power law. Yeah?
I know you said the ABJ anomaly was required to make this work, but is this required, or is it just something that we should worry about?
Well, right. So you, yeah, how should I phrase this? If the symmetry were really only broken by the ABJ anomaly, if that was the only term that appeared, then the Axiom would just solve the strong CP problem. And that's kind of what we aimed up until this point. But given that we don't really believe global symmetries exactly exist in the first place, and second, that this wasn't even really a global symmetry because the ABJ anomaly already broke it, if you're just kind of an effective field theorist, you would say, well, I should be allowed to write down things that break the symmetry because it wasn't really a symmetry. Okay, and that's what we're doing. And we're even kind of being generous by not writing down any renormalizable thing that broke the symmetry. I haven't really given you a good excuse for why I don't just write, say, a phi squared term instead of a phi star phi. That would just break the symmetry badly with a relevant operator. Even if I'm kind of generous and assume somehow that it's only broken by irrelevant operators, we're already going to have a problem. Okay, so how bad is this problem? Let's take f to be 10 to the 12 GeV, for example. If this little n equals 8, if I have a phi to the 8th over m Planck to the 4th, we can estimate the size of this term, and it's something like 250 TeV to the 4th, cosine of n theta plus phi pq. That's a lot of orders of magnitude bigger than m pi squared f pi squared. If n is 12, plug in numbers, and I get something like 73 MeV to the 4th times this cosine. That's about the QCD scale now. That's still not good enough because we need theta to be 10 to the minus 10 or smaller. So what you've got to do is somehow forbid all these terms, forbid or strongly suppress the coefficients of all these terms up to something like n equals 14. Okay, so that's why if you talk to some model builders, they will say they don't quite believe in the Axion because you need this really strong condition. Yeah?
Could you use the same mechanism to forbid all of the terms up to n equals 14? Or
Potentially, yeah. So let me now say a few of the things people suggest. And then I'll tell you the one that I think is actually reasonable, that might really describe the universe we live in. Okay, but first, what are sort of some options? Option number one, some kind of discrete age symmetry. Like say there is a Z15 symmetry under which phi had charge 1. Then I would be allowed to write phi to the 15, but I wouldn't be allowed to write anything smaller than that. Okay, that would forbid all the terms up to there. But I wanted to write phi q q bar, so I'd have to make the charges of q and q bar the right thing to cancel the charge of phi, and I would still have to think through all the other operators I could write that involve the q's, so it's not necessarily quite that easy. Besides the fact that where would Z15 have come from? It's sort of a weird thing to postulate in the first place. Yeah. Right, so why does it have to be gauged? You could say it's global, but again, I don't believe in global symmetries for reasons I'll tell you tomorrow. So, yeah. Yeah, so gauge symmetries can't be broken. So if we postulate a gauge symmetry, and then we're kind of, we don't have to worry about some subtle gravitational effect that's going to generate phi to the 12th or whatever. Okay, so that's one approach. Another approach is to have a composite axion. Okay. Just like if I want to estimate some high energy baryon number violating effects, I don't use the proton field because the proton isn't fundamental. I use the quarks, right? And so the thing that would make a proton, I have to use multiple quark fields, and so it's a higher dimension thing. If somehow this phi is really some composite object, it's sort of fundamentally higher dimensional, and that can give us more suppression. So, so loosely speaking, that's another way to kind of build in some automatic factors that are going to suppress these terms. Okay, and a lot of work has gone into both of those, and I am not going to tell you any more about them because I really want to tell you about option 3. Option 3 is axions from higher dimensional gauge fields. So this is going to be kind of a fundamentally different kind of model. We're not going to have a 4D Peccei-Quinn symmetry that we spontaneously break and get a Goldstone. We're just going to have some higher dimensional theory that's compactified down to 4 dimensions to get the standard model. And the axion is going to be a mode of a higher dimensional gauge field. This is an old idea. Models along these lines were discovered in the early days of string theory. And then later, in the early 2000s, there was this big wave of phenomenological particle theory model building using extra dimensions. And this idea was kind of rediscovered, or at least repurposed. And so there's a lot of different versions of this idea. But let me just talk about sort of the simplest incarnation, which is just to have a single extra dimension, which is a 5th dimension that's a circle. There are reasons why that's maybe not the best way to build the model, because when we have an extra dimension that's a circle, we also get a gauge field, which I don't really want. But this is the easiest way to illustrate the general theme, and then you can do similar things in higher dimensions that behave differently. Okay. So we're going to have a 5D theory with a U1 gauge field A. And we're going to compactify on a circle. So I'm going to have a 5th coordinate, x5, where x5 is identified with x5 plus 2 pi r. And when I compactify this theory to 4 dimensions, I'm going to get a field theta, which is the integral of A, my 5D gauge field, around the circle. Okay, so this is the differential form notation for that. Writing it maybe a little more explicitly, it's just the integral from 0 to 2 pi r dx5 of A5 of x and x5. Okay, so we just integrated our gauge field around a loop. That defines a periodic 4D field. So I will automatically get out of this a 4D field that has this gauge redundancy where theta is the same as theta plus 2 pi. Why is that? Well, we already saw that e to the I integral of A around a circle is a well-defined thing. That's our Wilson loop. Here I'm just taking that circle to be the extra dimension. And this becomes, in 4D, e to the I theta. So if e to the I theta is going to be a well-defined thing, then theta should be periodic with period 2 pi. Yeah.
R, like meaningful, like radial parameter or something?
Yeah, R is the size of the extra dimensional circle. Yeah. Okay. Good. So I start with the 5D gauge field. I get a scalar that's periodic in 4 dimensions. In fact, you can do this in higher dimensions. I could have, say, a 2-dimensional cycle in some extra dimensions, and I can integrate a 2-form gauge field over it, and I got an axion-like field in 4D. I could have a 4-dimensional cycle and integrate a 4-form gauge field. And so there's a whole family of these things, and they're all over the place in string theory. They're just automatically there. You don't have to put them in by hand. They're just part of the theory. OK, but the 5D case is sort of the simplest way to illustrate. In 5D, we had some kinetic term that depended on a 5D coupling constant for our U1 gauge theory. In 5 dimensions, this coupling constant, 1 over e squared, has units of mass. When I reduce to 4D, I get my axion kinetic term out of this, where this constant f squared in front turns out to be 1 over 2 pi r E5 squared. So if the 5D gauge theory is weakly coupled, and if the radius of our extra dimensions are small, which they ought to be if we're not going to have seen them before, then f can be big. Okay? And big F is what we want, at least big enough that it's consistent with the experimental constraints we have so far. OK, so that's how we start with the 5D gauge field, and we get one of our key ingredients for solving strong CP, which is a periodic scalar field in 4 dimensions. We had another key ingredient for solving strong CP, which was that we need that scalar to couple to gluons. So where can that come from? It turns out our 5D theory could have a kind of term in it called a Chern-Simons term. That looks like some integer over 8 pi squared, integral over our 5D space of our 5D gauge field A, wedge trace of our other gauge fields, G wedge G. This is a Chern-Simons action. And the Chern-Simons action is not gauge invariant, but e to the I Chern-Simons action is gauge invariant. If you haven't seen this before, I'm just going to kind of have to ask you to believe me that it makes sense to have an action like this, even though it isn't gauge invariant. The reason is very similar to the reason why we could get away with things like theta, trace G wedge G, or why we could get away with things like a Wilson loop that's just an integral over A. It's somehow the topology of the winding has some quantization built in that makes it OK to put it inside an e to the IS. Yeah?
For the kinetic term,
Yeah.
to go from the A to the theta, you need one integration. But you have 2 A's and 2 thetas, only one integration. How do
Yeah, so what we're really doing is we're kind of decomposing our 5D gauge field into a bunch of modes, and this is one of them. So it's like doing some Fourier decomposition of the modes around the circle. And then you kind of plug all of that back into the integral and you'll get that. So there is a little bit of work in going from one to the other that I kind of skipped over. But morally speaking, roughly what's happening is that theta is just like 2 pi r times a, roughly. And so when you take f, you divide by 2 pi r to get d theta, roughly speaking. OK, so I'm allowed to write this kind of coupling in my higher dimensional theory. And when I dimensionally reduce, it just turns into, well, again, there's a bunch of different modes. But if you look at the light modes, it turns into the theta times trace g wedge g that we wanted. OK, so the extra dimensional theory can naturally have kind of all the ingredients we want to solve the strong CP problem when we compactify. And in that theory, we didn't generate this Chern-Simons term by integrating out some chiral fermions like we did in 4D. It was just kind of there. And these terms are sort of naturally there in extra dimensional theories that we know about. OK, so how much time do I have left? A few minutes. OK. OK, so this is a way to get an Axion model with the right ingredients to solve strong CP. I had to invoke extra dimensions. You might or might not find that compelling. But what I want to convince you of in the last few minutes is that this model is much better for the Axion quality problem than any 4D model, or at least than any 4D model where you don't work really hard to make one of these things work. Yeah.
I can save it since we're close.
OK, thanks. OK, so why is this model better at solving the Axion quality problem than other models? It's basically because gauge fields are very constrained. Right, so my theta came from a gauge field. The 2 pi invariance of theta came from some underlying kind of winding gauge transformations of that gauge field. But when I have a gauge field, I can't just write down any random stuff that's going to turn into a potential for theta at low energies. I can only write down very specific things. Things that involve the field strength involve derivatives of the gauge field. Those are going to turn into things that involve derivatives of theta, and those I don't worry about. Those don't generate potentials. So what do I worry about? I worry about non-derivative couplings of gauge fields. Where do we see those? We see those when we have charged particles, charged objects. Right? So a charged field has a covariant derivative, like d phi, where the derivative along the fifth coordinate that I compactified on looks like partial derivative plus I times a charge times my A5, my gauge field, times phi. That's a non-derivative coupling of A5 that turns into a non-derivative coupling of my axion. And so charged fields in the higher dimensional theory can generate new terms in my potential for my axion. What do these look like? I get some set of modes, Kaluza-Klein modes. I think Raman at least has briefly used those words, Hiratazi. What you get is for a mode that has kind of n units of momentum around the extra dimensional circle, you get this fifth derivative turning into n over r. But now we have this extra piece that comes from A5, and when we compactify, that turns into a charge times theta over 2 pi r. And so the mass of a KK mode comes from a 5D mass plus a piece that depends on 1 over r, and it has a KK momentum that Raman probably told you about, but it has an extra piece that knows about theta. And so when I think about my low energy theory, I have mode theta. It talks to all these different things that are propagating around the circle through loops, and that generates a potential. Now this potential looks a little funny because this mass term didn't look periodic in theta. But physics is supposed to be 2 pi periodic in theta. the way that works is if theta goes to theta plus 2 pi, what happens is basically each of these modes kind of hops over and becomes another mode, and they sort of shuffle along. Okay, that's a phenomenon called monodromy. And there's a way to sum up the series of all these things and get a manifestly periodic potential. And that's using a trick called Poisson Resummation for summing series. There's another way to think about the Poisson resum series, which is to think we take our extra dimensional circle and we wrap a world line of charged particles around it. And you can think of that as a semi-classical calculation. What you get in the end is a potential for theta that goes like e to the minus 2 pi r times the mass in 5D times a cosine of q times theta. And I'm probably at the very limit of my time, even slightly over. So let me just say the key takeaway is that this is exponential. Basically, we have a massive thing. It's propagating over some distance around this extra dimensional circle to generate this effect. And so if you make the circle big, or you make the object heavy enough, you get an exponentially small propagator around the circle. Okay? And this is a general feature of all these higher dimensional axions. All their potentials are exponentially small. So in 4D, we were fighting an exponential with the power law, and it was a hard fight. But when you have these higher dimensional axions, you're fighting exponentials with other exponentials, and you've kind of taken the log of the axion quality problem. Okay? You still have a problem, kind of. You still have contributions you might worry about. But what you worry about is whether the exponent is, say, the other exponent plus a small number instead of, trying to just directly generate a tiny number. OK, so I'll stop there, and we can talk more about this tomorrow.
So before we go to lunch, I want to talk a little bit about Friday. So the organizers moved the lectures from the afternoon to the morning, hoping that would be easier because it was empty. Then a number of you told us that you had plans for the morning, which we have interfered with. So I apologize. We should have consulted the students before we made this. The organizers are willing to do it either way. So I can let the students decide if it's okay with the lecturers to do it either way. So the lecturers, are you locked into the morning now, or I'm flexible. You're flexible, and Daniel, you're surprised? Either way is fine. Either way is fine? Okay, so we're happy to leave it up to you all. I know there's a poll online. We don't just do a poll now. I think most people would care. Maybe we should just do that. If you don't care strongly one way or another, you don't have to vote. But okay, if you would really prefer